Static analysis is what your compiler does. So if you're familiar with C++, Java, any compiled language, it looks at your code in great detail so that it can write down the assembly version that the computer will understand. And so it does it statically, which means that it doesn't run your code, of course, because it hasn't compiled it yet. And so we're going to be talking about doing that in a dynamic language, Julia, which is JIT compiled. That means that while your code is running, it's getting compiled. So each function gets compiled, and then you can run it as many times as you want, as opposed to interpreter that has to do stuff on each thing to run it. So first I'm going to talk a little bit about Julia. Julia is a high-level, dynamically typed language. So you might think of Python or Ruby. One of the differences is that Julia is implemented as a JIT compiler, whereas Python and Ruby are implemented as interpreters, and there are some JIT compilation versions of Python. Julia is aimed at technical computing. So if you think of what people would use MATLAB, NumPy, SciPy for, that's the sort of niche Julia is aiming at. Julia is also general purpose, so anywhere you could use something like Python or Java, you can use Julia. And so the goal for us at aiming at technical computing is that currently you use two languages when you're a scientist. You use Python, and all of your Python code calls C libraries that do the really important fast stuff, which means that when you want to do something new that isn't already built into NumPy or MATLAB as a function, it's really hard for you to get that in there and make it really run fast, because you have to learn C and learn how to do the C to Python stuff. Whereas in Julia, you just write some more Julia that looks basically like the Julia you've already been writing. And so I'm going to show you sort of what some Julia code looks like in order to motivate so you understand what we're doing with the static analysis. So this is a type in Julia. Type is the keyword, the end keyword ends the block. Node is the name of our type. We're going to be talking about linked list nodes. So as you're probably familiar, a linked list is a kind of linked list. It has a sequence of data. Each node contributes to this by holding one piece of the data and a pointer to the next node in the sequence. So our node, we capitalize names by convention. You could type it lowercase and it'd be fine. Data is our field for data, and next is the next node in the list. So you'll notice that next has a type annotation on it. The colon says this is a type. So union of nothing and node means that this has one of two types. It's either going to be nothing, which is a type that represents sort of like a null pointer. There's only one instance of nothing, and that is lowercase n, nothing. The other option is another node, so our types can refer to themselves. So data does not have a type annotation. If I put one on there, it would be any, and these two things mean exactly the same thing. Any is the top of our type hierarchy. All types are descended from any, so you can put anything you want into data. So this is an untyped list. So to do some more Julia code, so if I wanted to type x equals 5, that would give me a variable x. Its value would be 5. In Julia, values have types. Every value has a type. Types are used to indicate how you're representing them in memory. But variables do not really have types. They share, they have a value in them that has a type. And so if I say x equals 5 and x equals node of 5, nothing, so this is the list of one element, it holds 5. There's no errors thrown from this. X did not actually have a type, it just happened to have a value of a particular type. So let's head over to the Julia REPL. So the REPL is very important to Julia, as in many dynamic languages. Being able to interact with your code really helps you understand what's going on. So we type in x equals 5, and it prints out 5 because everything in Julia is an expression, which means everything returns some value. Sometimes that value is nothing, but it always returns something. And in the REPL, it prints out whatever you returned. So in an assignment, we get whatever the value we're assigning is. So we can create a value. So we're creating a list of length 1 that holds a node. The default printing for a new type is the same as the way you would type the constructor. So that's why you have the same text at the prompt and print it out. And so we can make a longer list. This is what a list of length 2 is. So node of 5, node of 6, nothing. So you just insert the node right into the inline into the constructor. All right, so there's an important point in Julia that we haven't discussed yet, and that is Julia uses multiple dispatch. So in object-oriented languages, you use single dispatch. Your classes own their methods. So if X has a plus method, you write plus inside the class, you own plus And if some other type has its own plus method, those are separate methods. They are not one thing. They're something that has the same name but are owned by separate types. In Julia, as you saw, the types don't have any methods of their own. They just have some data. Instead, we have the functions. Any named function in Julia is generic. That means that it's a function that is composed of many methods. So the plus function owns all of its methods. They're all part of one thing that you refer to as plus. So here you would rewrite x.plus of y to be plus of x comma y. This allows you to add methods to plus without whatever type of x is owning them. So you wrote x, somebody else wrote x. It's in a library somewhere, whatever type you're using for that. Maybe it's in the base library. And in your library, you want to make it interact with some new type, but still in the plus function. And you can do that. So here's an example. So we're mathematicians. We're doing technical computing. We're writing our own numeric type. It's called myType. And if we were doing this in an object-oriented language, we would, we have a class myType, and the only thing I'm showing you is the plus method that we're adding to it. So this, something of myType, and then an int, and we're doing something random inside that returns a new myType. So we got one direction, so myType plus 5. Good. What if I write it the other way around, 5 plus myType? Well, then my types go in the other order, and I'm going to have to do something fancy. Like, some languages, there's more or less of a way to do this. In Ruby or Python, maybe you would monkey patch the standard library. That sounds pretty crazy. That's not really what I want to do. In Julia, you would write two functions. So I put some type annotations on here. This is for multiple dispatch, so other people can have plus things, and I'm not messing up their two-argument plus methods. So here, the first one takes myType and then an int, and then the other one takes the opposite order. These functions could appear next to each other in my file, in some other file, in separate files. You can write them wherever you want. If I wanted to add more types, I can just write the new methods. And this plus function that we're extending is the base plus function. So this is exactly the same addition you do with everything else. And any code that only depends on the types involved doing addition will work with these methods. It doesn't have to know anything about who defined what. So now that I've shown you a little bit about how Julia works, I'm going to talk about static analysis. And so we're implementing static analysis for Julia. Julia is JIT compiled, but it doesn't do any type checking or anything during compilation. It only uses the types to optimize things, and it does infer the types. But we want to add some static checks so that when you're writing a big library, you can be sure that you haven't made some of these errors. So when we're doing static analysis, we have to decide what we're going to check for. So what problem do we want to help people with? Maybe my problem is that I sometimes mistype variables, and sometimes my code just doesn't always make sense. So I try to I put something in my sum variable, but sometimes I misspelled sum because I've been looking at the same word a dozen times, and I don't really spell it right anymore. So then we have to decide exactly what we're going to check for. Are we going to check for when I misspell it once and I just have this variable that I'm just sort of setting it equal to something, and it's clearly I'm not using that variable, so why did I do that? So I'm probably doing something wrong. So that means that we're particularly checking for assigning a value to a variable that I've never used before or since. And then after that comes some implementation details. So how do I find the assignments? How do I find what values? How do I find the name of the variable and whether it's been used before or not? And the implementation details covers digging into the data structures that are exposed to us that we can use to understand the code, and all of that sort of actually writing and testing the code. So the focus of this talk is mostly going to be deciding exactly what to check for, because I already decided, what to check for because I picked to put them in my talk. And the implementation details we're going to brush over, but aren't super interesting, all the bugs that I had when I'm trying to get my code right. So mostly what we're going to talk about is exactly how we're going to solve a problem by checking for it. So TypeCheck is the package I wrote for Julia. It's a normal Julia package, so we're doing static analysis code of Julia code through writing Julia code. So there's nothing extra that we're just using normal Julia. We're using static analysis to check for problems, which means your code is not going to be running. We're just going to look at it. And you don't have to change your Julia code in order to use this. There's no extra annotations, no effort on your part. You just take it and run it. And the inspiration for the checks are based on problems people have. They go to the mailing list, they go, why is my code slow? Or can you help me figure out where my bug is? They go, okay, we can help. We can automatically help. So a couple of points here before I start. So these are going to be sort of repeated throughout the checks. So we're trying to only warn when we know something is wrong. So you're probably familiar, you compile with all the warnings on, and there's these 5 warnings that this file always gives. And so you go, no, it's okay, I can ignore the 5 warnings, I don't really care about those. And it's really hard to count, you don't read them in detail, so it's hard to tell when there's like a 6th one added in there that you actually care about, and you're like, oh man, I wish I had seen that before I spent an hour debugging my code. And so we're trying to only have warnings when there's actually something wrong so you don't ignore them. Another thing we're doing is, so Julia has built-in type inference. I am not doing type inference. I'm only reading the output of the type inference that Julia already provides. And so beyond avoiding duplicating a bunch of work, because Julia's compiler is type inference determines the way your code will actually run, that's all that we care about. We don't care about what I might think about the types. It's just what Julia thinks. And the other point is when I'm doing these checking functions, all of them are going to return a type. So I'm not going to print out the warnings. I'm going to return a type that when you print it will show you all the warnings. That makes it easier for other people that aren't me to write a program that checks their code and looks at the error messages and decides if they have warnings. And you can stick it into some other interface that I don't know about, and you just go, yeah, I can just grab the results of those functions. So I'm going to tell you the 3 checks we're doing, and then we're going to go through each one in more detail. So checking loop variable types. So this is about, so you use a variable in a loop, and it has some type. Sometimes as you go through the loop, you might change the type of your variable. You don't want to do that. It makes your code slower. So we're going to look for that, and it can be hard to tell for programmers whether that's a problem for them. No method errors are a kind of error in Julia. As you might expect, there's no method that handles this type signature the way you're calling it. So we're going to try to statically detect those as a way of type checking statically. We're trying to predict them. Spell check is the one I mentioned before. So sometimes I mistype my variable name, and if I mistype it once, we're going to try to catch that, because it can be pretty frustrating when it just doesn't work right, and you're like, I'm sure my algorithm is right, but the output doesn't make sense. So checking loop variables. So in Julia, we care about performance. We want to be able to write Julia code that's at least as fast, within 2 times C. And once you optimize it, it's usually between like 1/2 and 2 times the speed of C++ would be. So one of the things that can often trip up, especially newer users, is having type stability. So this can actually be a subtle difference in your code, but it affects your performance a lot. So it makes a difference in both your runtime and also in the amount of memory you allocate. And so we're going to look at the types of variables in your loop for you so we can tell you that you have a problem and which variable is the problem. And so this is in Julia code. So there's 2 functions here, one on the left, one on the right. They do basically the same thing, but on the one on the left is type unstable. So I'm going to read through the code for you and then tell you what the types are doing. So sum is equal to 0 for I is 1 to 100. So I is going to take on the values 1 through 100, counting by 1. So 1, 2, 3, and then ending at 99, 100. And for each value of I, we're going to say sum is equal to sum plus I divided by 2. So, and then we're going to return sum at the end. And both sides do that. So on the left, we have sum equals 0. 0 is an int64 literal. So that's always going to be, so it's an int literal, so if you're on a 64-bit system, 64 bits, 32 bits on a 32-bit system. But so you have, sum is an integer. I is an integer, because that's an integer range 1 to 100. We divide I by 2. That's a float 64. It would be called double in C. So it's a floating point number. We add a float and an int, we get float 64. So sum has changed type here. Its value was an int, and then the first time through the loop, it changes to have a value that's a float 64. For the rest of the loop, it's going to happily be float 64s all the way through and return a float 64. On the right, in B, we have sum equals 0.0, 2 characters different. 0.0 is a float 64 literal, so sum is going to start out as a float 64 and stay that way the whole time. So sum's type is stable in B. It does not change during the loop. So what we're going to do is, as you see at the bottom after the ends, we're going to run run them once, and that run is going to be compiling the two functions, and then we're going to use the @time macro to time them. So the @time macro prints out the elapsed time as a side effect, and then you'll still get your normal value back. So we can do @time of A, and we get the elapsed time. We also get the answer, so 2,525, same in both of them, so another clue that they're the same. However, if you look at the times, A is in 9.5 microseconds, B is in 2.2 microseconds. Only 100 times through my loop, really, really fast, both of them. Can't really read that much into the numbers. A is, it looks slower. But you go, whoa, look at that memory. We're also getting bytes allocated as part of the output of that time. And A has, like 3 kilobytes, and B has 64 bytes. So this looks pretty weird beyond, even though I'm not reading that much into the times. So why would A have more memory allocation? And so, the first reaction is, well, did I run A first? Like, I double-checked, I ran it again to make sure. But this is the actual output. And so to make sure that it's the loop that's the problem, we can run an experiment. I'm going to change A. I'm going to add 2 more zeros to that loop. So we should give out like 100 times more memory allocation if that's the problem. So run A, get a new answer. That's us compiling A. And then we run it again. So this is the compiled version. And it uses about 100 times more memory. And so just to be clear, this bytes allocated is not a high tide mark. At no time was my program necessarily using this much RAM. So in Julia, as you allocate things on the heap, you're basically calling C's malloc under the hood somewhere. So every time you call, you're going, okay, I'm allocating this many more bytes, and you're adding up to your sum. And at some point, the garbage collector is going to come through and vacuum up the memory you're done with that you just dropped on the floor. But we're not going to reduce the bytes allocated. So this is just the total. It goes up the whole time your program goes through, even as the garbage collector reduces the amount you're actually using. And so that means we spent time allocating all of these bytes of memory. So I know this looks more intimidating. You can't read it. It's just like some small text. So this is the output of code typed. Code typed is a function in Julia. It's a built-in function. As part of a set of functions Julia has for looking at different layers of the compiled code. So you write some code, and then it goes into the compiler, and it goes through several different representations as the compiler works through it before it gets to assembly. And so this is one of the later phases in Julia. So this is after it's been type inferred and optimized. So we've rearranged it a bunch. So it doesn't really look quite like our Julia code, and it has a lot of type annotations in there as the type inference writes down its work as it goes. And so I'm going to zoom into parts of this output so that you can actually talk about it. So this is on the top we have the output for A, on the bottom for B, and this is a list of variables used in the function. And so one of them is at the top is sum. So we have the name of the variable sum. We have its type, which for A is any, and which for B is float64. So this is the time that the type inference is going, sum has a problem in function A. It has multiple types. So the type inference could have like a tighter type on this if it wanted to, but this is going, what does it matter? It's multiple types. I'm just going to give up and say, any will cover all of the possible types it has, but you're definitely not a concrete type anymore. And so this is the rest of the output of code typed, or most of it. And in orange, I've highlighted the usage of sum. So you can sort of see at the beginning, we set the value of sum. In the middle, that's the reference to sum in the loop. And at the end, we're returning sum. So sort of 3 references as you had in the original code. This in blue is the loop, and in orange is the middle of the loop where we actually make the addition to sum. So the blue is just the stuff at this level of AST that you have to do to increment a loop variable. And this is the same output for B. Very similar, just slightly different. And it all looks really similar, but there's a problem with these types. So I'm going to zoom in on this orange line. So on the top, you see how A is adding things to sum, and on the bottom, you see how B is doing it. That whole blue blob is just it going, I have I know I is an int, I'm dividing by 2, I know what 2 is, it's an int, I'm going to end up with a float, and it's, it's talking itself through very carefully what it's doing, and that's what the whole blue part is. So that you can just make, that's just I divided by 2. It's exactly the same character in both of them. So on top, we have the A version. So sum equals Sum is of type union int64 float64 plus, and so this in orange is the multiple dispatch plus because we're not sure which one we're using. And then we have I over 2. And so on the bottom we have sum equals, so top of box. So top is the way the AST writes down, I'm using an intrinsic function that's not just a normal Julia function, it's an intrinsic function that's implemented in C and appears as a Julia function. And so box is saying, I'm going to box this value as the first argument, so float64. And then we have add float, another intrinsic function, and we're going to do sum plus I over 2. And we know that they're both floats, and we're always going to get a float back, so we can use these intrinsic functions. And so why is this actually slower? Why is this top version actually causing us a problem? And so we need to know some things about how Julia works to understand why this is slow. You don't have to understand why it's slow to use it and go, I'm just going to fix the warning, but probably interested in why it's slow. So Julia has two kinds of types. There's concrete types and there's non-concrete types, so either an abstract type or an unstable type. So concrete types means you know exactly how you're representing them in memory. So it's an int64 or a float64. We know exactly what operations we do to add them together. Non-concrete types mean, you know, I'm not really sure. It might be mutable. Somebody else might have a pointer to it. It could be an array. Who knows what it is? And so if it's not concrete, you allocate it on the heap. So you're allocating memory, and if it's an immutable type, so immutable types are value types. So like most numbers are immutable types like ints, where if you change the value, you should get a new instance of it out. So if you add 2 plus 5, you don't want to change 2 or 5. You want to get a new number that represents their sum. And so immutable types are often nice because you know that if you have one in your function, it knows that it can, you know, copy that someplace else, like maybe put it into a register and start mutating it, because nobody else is going to have a pointer to it where it's going to change. However, if you have immutable types and you don't have good type inference, then it's going to say, well, I have an immutable type. I can't change it. It's on the heap. Okay, I'll need to make you a new box on the heap to hold your new result. And I'm going to have to do that every time through the loop. So it's going, I didn't really know what sum was, so you know, not only am I branching in my code to decide how to add it together, I'm also going to make a new instance of it on a heap every time. So this type instability is leading us to a lot of small allocations as we make a new box every time through the loop. And so you can see this complexity in the assembly code. So code native is another function built into Julia saying, okay, I want the output of LLVM, ask LLVM what the assembly code for this function looks like. And so for A, we get 2 columns of tiny text. It has to do all the stuff to decide what plus and to pull the values out of memory and everything. And this is for B. The text is bigger, there's 1 column. This is just doing the actual float division and addition. And so this is a lot shorter and simpler, and this is like another sign that this function is probably doing better. So to actually run this check, if you had some Julia code that you were going to run it on, so definition of A is over on the left. If I run checklooptypes of A, I'm going to get, so it's telling me the function name A. The method takes no arguments because it's running on all of the methods of A. I've just only defined one. The return type of A is union the float64 and 64 because it's not really sure what the type of sum is at the end of the loop. And then sum has type. Sum is the variable that we're having a problem with. This is indented, so you can tell it's one of the variables, possibly multiple, in our function, and then the type of sum. And these are all the inferred return types, inferred types of variables. So we're going to move on to the next check. So this is no method errors. So this is a runtime error. It's what you would see sort of as a type error. Is you're calling a method, and either the order of your arguments isn't right, or their types are just wrong. So of course, I want to know statically. I don't want to have to run all of my code through all of the code paths and make sure I have perfect test coverage to make sure this works. I just want to, ask at compile time. So this is especially important for little used portions of your code, because you'll get an error pretty quickly, and you will see a runtime error, and it's a pretty good error. It just doesn't happen until you run the code. So this is another way of writing functions in Julia. This is a one-line function. So another function A takes x. X is going to be an int, and I'm going to mod x by 7. Pretty simple function. This one's totally equal. B also takes an int. This time it divides x by 2 and then calls A. So that's our only method of a that we wrote up above there. We've already heard in the first part that x divided by 2 is a float 64. So we know that a is getting called with a float 64. So we know that this is going to be a no method error because we know the methods of a, we know what b is calling it with, and we go, that's not going to work. And so because we can look at the code and use knowledge that the computer would also have to decide this is a problem, the computer should be able to decide this is a problem. So we know that it will know that division of 2 ints is a float 64. The compiler already knows that. And we know that a of float 64 will cause no method error. It already knows the methods of a when it compiles the code, although it's hopeful that you'll later define a method of a that will work here. But it knows that there isn't one. So I'm not going to talk more, because the rest of this is just implementation details of how do you see, there's a function to get the methods, how do you dig in programmatically to the methods, and how do you read the inferred type of each of these various kinds of expressions in some undocumented data structure. So while that was an adventure, it's not especially interesting now that I have the code that does it. So I'm going to talk about, this has actually resulted in more errors filed on base. So base is our standard library. It's pretty high quality. They're pretty careful about only putting stable things into it because everyone who has Julia has the entire standard library. It has lots of math, and it really is pretty big. So there's some dustier corners where people don't run that code as much, and so that gives us an opportunity with this code to go, I can find some errors that people haven't found yet. And so one of them, so this is QRFact. I don't really know what it does, but I know this has a problem. So this is most of the QRFact things. It's a math thing. It does stuff on matrices. But they had a method that handles numbers. So number is an abstract type. It has numbers in it. Int 64 and float 64 are some of its many subtypes. And so it calls this other function QR, and it calls QR with fill of these two fill functions. And so fill will give you back an array that's filled with, I think, filled with ones. So anyway, it's creating two arrays, and it's calling QR. So methods of QR, it only has one method. And so in pink, you can see you have this first argument. So it's filling something, and we're hoping that's a matrix. So an array of T2. And so the T is just a type variable. So that would be the type that's in that the matrix is holding. And 2 means it's two-dimensional. So rather than having arrays of arrays in Julia, we have multi-dimensional arrays. So these are type parameters. So this is a type parameter on the first argument saying that it should be a matrix. And then you see a very similar type in yellow for the second argument. And that's saying that it should be a vector, so a one-dimensional array. So there's a T on QR and a T in each of the arrays. And this is QR requesting that the two arrays have the same type in them. OK, so let's try calling it. So we can make a number pretty quickly. That's a 2. So any number will work to get to this method. And so we get a no method error. So this is what an actual no method error looks like. Error, no method. And it's saying the problem is QR. You're trying to call QR with two matrices. So in the yellow, you see the type has a 2 in it so over here we went QR wanted a 1, and we gave it a 2. And it helpfully tells us, where QRFact is defined that we're having a problem with. So this is the problem. So this is the problem. This is how I described it to the bug report. I think they fixed it by removing this method because they decided they didn't actually need it. But they had they'd refactored previously, so they didn't really need it anymore. But they just sort of missed this one, and it doesn't work. And they're like, oh, whoops. So minor bug, but it might have caused somebody a problem someday when they accidentally called number thinking it would work. So more tiny code. I realize it's unreadable. I just want to show you the whole block of code that we're looking at here to give you an idea of what you would actually look at if you were going through by hand and trying to find these issues. The issue number in the slide, by the way, is so if you wanted to look it up on the GitHub issues on the Lang Julia repository, you can find my issues. They're real. So we're zooming in on the code. So I removed some of the other loops. We're just looking at the one where the problem is. And so for up, in, plus, minus, so that we're defining we're going to find plus and minus functions for these things. And so the 2 for loops inside that, so this is one of 3 blocks of nested loops. So it's going through this list of special matrix types. So in Julia, types are first class. You can just use them. You can like have a list of them, and you can do stuff with them, and they're just normal expressions. It's one of the advantages of being dynamically typed. So we have an @eval block. So Julia has macros. So is how you call a macro. So @eval, eval is the name of a macro. And then we have a begin-end block. So that makes this whole block get passed into the @eval macro. And so, all right, so we have $op. So we have our op variable. This $sign is saying interpolate my variable value into this block. And we often use $signs to interpolate things into blocks or into strings or into anything. That's just our interpolation syntax. And so we're saying we're going to define two methods. They're all going to be A and then B. So matrix type 1 and so the first one we have matrix type 1 and matrix type 2, and the second one we reverse them. So we're making sure our plus and minus work both ways. And all we're doing is we're converting the less dense matrix type, the sparser one, into the more dense form, because generally you can do that. And so sparser means that it takes you less data to represent the whole matrix, and a denser version, so the most dense version is just an entire array that's just a solid block of memory holding all of the numbers that go in your matrix. But if you have something like a diagonal or triangular matrix, you can go, well, I don't really need all the numbers, I only need the ones that I know aren't 0. And so you can do something fancy. But then you have these two types, and you don't really want to define plus and minus for all other possible matrix types. So they're defining the conversions here. And that's why they call a convert function in both. So we're generating code. This is a risky sign. We're generating code, which means we don't know exactly what it's generating. So this is the list of generated methods that will call a no method error if you call them. So there's a bunch of them, but because this is generated code, we know that that the problem is probably going to be a pattern. And so, sure enough, triangular occurs in all of these type signatures as either the first or second argument. So it's bad either way when it appears. And so if we dig in further, so I like to actually call the method to find out what actually happens. So I figured out how to make a triangular type. This is just like some random value. You look at the signature of the constructor and you construct one. It was actually hard to figure out what the symbol at the end is supposed to be. It's either capital U or capital L for upper or lower. So I have a triangular. I can make a diagonal by converting a triangular to a diagonal. And so I have the two correct types. I can use the @which macro. So I do D plus T, and so I'm hoping to call diagonal plus triangular. And I'm using the @which macro to confirm that that is actually the method that's going to get called. So it's telling me the signature of the method and where the method is defined that I'm calling. So I'm going to call it. And we get a no method error, as I was hoping. And this no method error is that triangular doesn't exist. And all of those definitions we saw those were all the ones where triangular is the more dense type. So we're converting the other one to a triangular and trying to add them. And sure enough, if I actually add two triangulars, it also gives me a no method error. So they fixed it. They defined plus and minus on triangulars, and they're actually this one had a bigger impact than that. They're considering refactoring how they do this plus and minus because Julia is a growing language and they have new features and they've discovered a new way of doing things. They're like, maybe we don't need to generate code to do this. But my favorite comment on this issue is actually, thanks for going through all the linear algebra code, by the way. It's no mean feat. This is a core Julia developer telling me, thank you for looking through all of our complicated linear algebra code. So, I did immediately correct him and go, type check, I wrote it, it's really cool. But I had the opportunity, I got some extra credit for, just running my static analysis, which takes a minute or two, finds all these problems. So if you too want extra credit for filing obscure issues, this is how you run check method calls. So we have A and B. I'm running it on B. So you set the module. I haven't quite figured out some of the namespacing issues, but you set the module name to the name of the library you're testing. So base for base, main if you're in the REPL defining these things. And so it tells me, B has a return type of any, and it has this problem where it's calling A of float 64. It does not have a return type on A because we don't have a method of A, so we can't infer a return type. That doesn't make sense because we don't have anything. So the last one, misspelled variables. So these are two functions. One of them has a problem. This is only 11 lines of code, but already, you have to look through all of it to decide what the problem is. This one actually isn't terrible because it will throw an error when you run the code because you're reading the value of a variable without having defined it. But it's a little hard to spot. So on the left we have correctly spelled answer, on the right, or the incorrectly spelled answer on the right, left, and then the other one is correctly spelled. And so we can tell, like, even if we didn't know what the code is supposed to do, we're probably pretty sure that that one inside the loop is wrong because it doesn't match anything else, and we never use it again. So we'd like to help out people who happen to have code, maybe 100 lines of code where they've sometimes misspelled a variable. And it's really hard after you've written like answer 24 times to tell when you've misspelled it because it doesn't even look like a word anymore. So first we have to talk about how we use variables. So we can use them on the left-hand side. So x equals 5, we're using x on the left-hand side. These are all involve an equal sign, assigning a value to a variable. On the right-hand side, we have x plus 2 or y equals x plus 2. So here these are both right-hand side uses of x. So you're reading the value of x. We can also do both in the same line. We have x plus equals 2, so that equals x equals x plus 2. So we have, it appears on both sides. So one thing we can do is we can make a function that collects a set of left-hand side usages. This is pretty easy. You go through the AST, you collect all the expressions that are equal sign assignment expressions, and you look at what they're assigning to, and you go, okay, I found all of these left-hand side variables. And then you make another one. It's going to collect right-hand side usages. This one is actually harder because you have to dig in deeper into the expressions to go, are you using a variable? Are you using a variable here? What if I dig in further into your return statement that has several nested function calls? And so you have to go in further. But that's also not too bad. And then what you do is you can combine those two functions. So you get the union of these two sets of usages, and then you get the intersection of them. So you have the union of them is all variable usages, and the intersection is the ones that you use both ways, where you both write and read the value of the variable. And so that remainder is the stuff we only use one way or the other. We might have assigned multiple times, but we never read it, or we read it, but we never gave it a value. The assigned but never used are actually more concerning because they're more likely to call you a hard to debug bug, because they're like, your code runs fine, it just gives you the wrong answer, as opposed to going, undefined, you have an undefined variable, that's a problem. So this doesn't cover x equals x plus 2. We could write a somewhat more complicated function that goes through and says, this line, it's going on both sides, but we can only count this as one usage of x. And goes through and counts your usages instead of deciding whether they're on the left or right side. But I haven't implemented that. That's just, that is another thing you could do to catch this. This isn't super important because you're reading from x, so x is probably undefined if you've only used it once, so you're going to get an error. So it's not like the worst kind of variable bug. So if you wanted to check your locals, you could check, you give it a function, so bar here, and it will give you a set of symbols. So if you look at the implementation of our function, we have y equals x, which is a argument, plus 2 plus z, and returning x. So why did we set, we probably misspelled y in the return statement. I know it's only one letter, but you can still misspell it. So we get the results of y and z because we assigned something to y but didn't use it, and read from z but didn't assign it. And so in conclusion, you should try Julia because you can write introspective code really easily relative to other languages. I use the parser, I use the type-inference, I'm just looking at some data structures, some undocumented data structures, but data structures provided by the base language. If you're not so interested in writing introspection, you should try Julia because it's fun to write. And once you've written some Julia, you can run TypeCheck on it, which is even more fun. And once you're running TypeCheck, you should write Julia code that consumes the result of TypeCheck. So we're statically analyzing Julia code using Julia code, and you should take the results of that and analyze them further using Julia code because I returned values. All that stuff we were printing out is just how you print the value that I returned. So you really are getting a value that you can pretty easily conclude as to whether you have problems with your code. And so that's my conclusion.
Yeah, I have a question. Actually, two. You mentioned Python at the beginning,
Yeah.
and then didn't cover anything about it. I was curious, it seems like there's things in Python that you could use to do similar such, but I didn't know if there was like a similar piece of work going on in Python. Yeah.
So I don't know a lot about Python. I only know that it's pretty similar to Julia, and I've used it a little bit. One of the things the difference about Python is you often, like when you're calling functions, you often represent your code as a string. And so I'm not sure what access they give you to an AST. You'd also have to decide whether, like, I don't think Python by default like infers your types for you. So if you're doing some of the type checking stuff, that you have to pick something that infers the types for you without running the code if you're going to do it statically. But yeah, I haven't done that much Python, so I don't know what the actual implementation challenges would be.
Yeah, I don't know. I was just curious because I've been sort of thinking about the same sort of thing, and we use Python at my work. My other question was, and you kind of mentioned it right there at the end, but do you then deploy this in some programmatic fashion to actually introspect your entire code base, or are you sort of doing it, are you writing unit tests as needed or something of the sort?
So the way I've been running, I already have functions in there to run it on a whole module. So usually in Julia, your package, is in one module that has the same name as your library. And so you can run, if you run any of these functions on a module, it will run it on each function that you've defined in the module and run on each method of those functions. And so you can run it on a whole module and get all of the results. And because they're programmatic, I haven't written the code to hook it up to something like, hook it up to Travis or hook it up to something else. But you could easily hook it up to anything that wants to aggregate your test results and also aggregate all of these static analysis warnings. Or, plug it into your editor or anything you want to do. Thank you.